So many presentations have already touched on the fact that, or today, that flooding and erosion risk on the coast are often driven by the combined effects of storm surges, high tides, and large wave events. And on the west coast of the United States, these extreme events are also exacerbated, if not driven by the El Niño Southern Oscillation, which can increase water levels for months at a time and change the direction of wave impact to the coast, causing hotspot erosion. So because of this, we're investigating the role that climate variability has on these extreme total water levels, and then also how this climate variability might change into the future and affect future water levels. So we're working with the U.S. Geological Survey, and they currently have in place a methodology for evaluating storm-induced change on the east coast of the United States, where they take some category of hurricane or storm and compare it to the backshore morphology and assess a probability of coastal change or response on the coastline. However, there really isn't a regionally consistent way to do this on the West Coast. We don't have hurricanes, and we have large-scale climate variability that affects storminess. So we're working on coming up with that methodology by looking at extreme total water levels, so for example, the 100-year event instead of categories of storms. And our pilot study areas will be the Rockaway Beach littoral cell in Oregon and the San Francisco littoral cell here in California. And today I'll focus on Ocean Beach, an area just west of here that has had erosion in the past and a lot of work done on this area already. So Fernando already kind of showed you these time series. Get my laser pointer. But we have water levels that we've extracted from the San Francisco tide gauge data and all of our water level components down here, and then our wave climate that we've extracted from the Global Ocean Wave Reanalysis data set out of IH Cantabria. And when we combine all of these parameters for here in San Francisco, we can get a total water level, where traditionally to evaluate extremes, we can take the most extreme events here, fit them to some extreme value distribution, and extrapolate the 100-year event. However, this doesn't give us, or rather, this only gives us the combination of events that have occurred in the past. How do we know we've seen the largest waves occurring with the highest tides? So in order to get around this problem, we've created a full simulation model that probabilistically simulates each of the different total water level components, recombines them back together to get what could be the most extreme water levels that a location could see. And so I don't really have time to get into how we model every single total water level component. You can read our paper if you want to know that, or talk to me after. But I do want to mention that we properly model our extreme components like wave heights and storm surges by fitting them to non-stationary extreme value distributions that include the effects of seasonality and climate indices, like the Pacific North American pattern, or the multivariate ENSO index. And these are really what's incorporating these climate change, or this climate variability, into our model. We also want to take into account that water levels and wave directions can be changed for months at a time, so this non-extreme component of the total water levels. And so we do this by also fitting these monthly mean sea level anomalies and these wave directions to some climate index. So here we have the multivariate ENSO index and the monthly mean sea level anomalies on the x-axis, and you can see that we can fit some kind of line to this and then simulate from the distribution around that best fit line. And this will allow us to get higher water levels during the extreme El Niño related years. We do this for wave heights and wave directions. So we simulate 500-year long time series, and this gives us a way to empirically extract the return level event rather than extrapolating it forward in time from some short time series. And so once we have our distributions, we simulate these climate indices to be 500 years long, but keep them having the same frequency of El Niño events, or major El Niño events, and then we simulate each of our wave and water level parameters. We then get our total water levels by extracting the morphology data, computing our wave run-up, and then we have multiple synthetic realizations of total water level time series. So again, I'll just show you, here is our example historical total water level components. And here in orange, I've just plotted one example synthetic simulation. And you can see that we pick up this seasonality that is true to each of these parameters, and also this interannual variability that is driven by these large-scale oscillations or climate oscillations that allow for more extreme events in certain years. So now that we have this methodology, we can apply this to Ocean Beach here in San Francisco. And so we run 35 500-year daily maxima total water simulations. And then we also extract the geomorphology from LiDAR data. So we have a beach slope, dunar structure, toe, and crest. And we've binned those all into 500-meter bins along the coast that have at least 20 transects per bin. And so we can run these simulations, again, an average return level event for the 10, 25, 50, and 100-year event. And just the darkness of the blue relates to a more extreme or a higher total water level magnitude. So you can see that we have some spatially varying total water levels. Well, what does this mean when you relate it to what's actually there behind in the backshore that the water level is actually could be interacting with? And here we just quickly show these events compared to, or using the storm impact regime from Salinger, where we're just looking at overwash here, and red values show areas that the water level is over the dune crest, so that we have, that's an indicator of flooding. And so you can see as we get, as we move over in extreme events from the 10 to 100-year event, certain areas become subject to overwashing that aren't for these smaller return level events. So this gives us an idea of, number one, how total water levels vary spatially, but what we can expect based on our past, or rather present day climate. However, we know climate is changing, and so we want to start considering how will these total water levels change into the future. So we run a couple or a few future climate scenarios for the end of the century, so 2080 to 2100. The first climate scenario is we allow changes to significant wave heights into the future. And right now we're not really sure how significant wave heights will change. These are just some examples of statistically downscaled global climate models. And we can see that some areas, they say waves will increase, some they'll decrease. So we allow for both to happen. And we do this by just shifting. Here's just an example. The orange is a simulation. The black is the observational record, and we just shift our distributions in either direction. And for the extremes, we would add a linear trend parameter to that fit. So this allows us to look at how wave changes could impact future climate. We also change the frequency of major El Niños, and these are allowed to double or halve over the 500-year period. The third scenario, we allow changes to sea level. So we have 3 sea level rise scenarios from the National Research Council. And these are sea level rise scenarios that include regional tectonics in the area. And these range from about 30 centimeters to 1.67 meters by 2100. And then our last scenario, we include all of these different pieces. So I'll just be showing you these maps, a few different maps like this, but on your left-hand side, we'll have the total water level, and so the darker blue indicates a higher water level event. And on your right-hand side, we'll have these, the overwashing on the coast. And up here in the corner, I just have the percent of the total coastline that's overwashed. So you can see for this historical event, about 7% of the coastline will be subject to overwashing for the average 100-year event across these 35 different simulations. We can then look at how changes to significant wave heights might change this average event, and you can see that in some areas we get some darker blues, so higher magnitude total water levels, but only about still 7% of the coast is, on average, affected by overwashing. Oh, and I also should mention that this on the side, we're running in the parentheses, we're running 35 simulations, so we're also looking at the maximum level of the coastline that could be overwashed and the minimum level based on those 35 simulations. If we add changes to the El Niño Southern Oscillation, where we're allowing this to decrease and increase, we can see we actually have a slight decrease of the total percent of coastline overwashed, so now about 6% of the coastline is overwashing, but we also have at this higher end about 8%. So it does have the potential, because we are doubling El Nino events in there too, to increase overwashing on the coast. We also add in these effects now, just look at sea level rise, and now all of a sudden we jump up about 10%, and about 17% of this coastline is now subject to overwashing, but it could be as much as 36% of the coastline. And then finally, as you might imagine, when we add these all together, we get the maximum amount of overwashing on the coast, about 20%, and this again has a high end bound of 36%, but I also want you to notice it has a low end bound of about 8%, and that is higher than what our projected 100-year return level is right now. So that's saying that if all of these different changes to the climate happen, then we might be looking at higher, or even at the low end of the spectrum, higher return level effects on the coast. So this gives you a good idea of how the coastline might vary spatially, how these total water level events might vary spatially, and what those hazards might look like on the coast to the development there. But we also really want to start thinking about not only how climate variability affects the total sum of these water levels, but how it affects all the individual components of these water levels. So here's just this average. In one of those bins, the average total water level event is about 5.8 meters. And here we've broken up the percent of contribution based on the different parameters that make up a total water level. So down here we have the wave run-up, which is a wave-induced component, the tide and the non-tidal residual, which includes storm surge and monthly mean sea level anomalies, and the seasonality. And you can see that the wave run-up has a huge contribution to the total water level in this area. And that's because on the West Coast we have a very high energy coastline. We then can throw on the rest of these simulations, and these colors just correspond to the different magnitude of the total water level we're looking at. But I most notably want to point out that while wave action really dominates the contribution to the 100-year total water level event in this area, as you increase sea level, that starts to lower a little bit, and you get this up to 22% of the total water level contribution from sea level rise. So really what we're trying to get at here is not only look at how the climate and future changes in climate can impact the spatial distribution of total water levels on the coast, but also how all of these different parameters that are influenced differently by different climatic forcings might change and really start to tease out what could be the most important climate changes for this region for these parameters. And so in summary, we used this full simulation total water level model. We generated many different synthetic time series for these historical and future climate scenarios. We know that this climate variability plays a large role in future coastal flooding. So if we pull this apart, maybe we can understand the drivers of these events a little bit more. And then here in Ocean Beach, while the wave action dominates the total water level, the sea level rise really increases by 22% in this relative contribution, and this leads to 10% more of the coastline being affected by overwashing on average. And so that's all I want to say today, and I can take questions or we can talk after the session.
I think we have